It went.
Well, we'll find out directly. Now then, we proceed with our considerations in regard to chemical effects on solubility of salts like calcium carbonate, which are not particularly soluble in water. The chemical effect which we will now examine by experiment is that of ammonium ion on the solubility of calcium carbonate. With that, we'll take a look at calculating the solubility of calcium carbonate at 1.0 molar ammonium chloride solution. After we do that calculation, based on the results, we'll calculate the hydronium ion concentration for the system. What can we at that point do to assess the validity of our calculations? Or do you believe that chemists, scientists are so good that the calculations which they do to resolve problems are always correct? I say to you, as I've said before, from my perspective, there's only one bottom line dictator in the world of science. And that is the experimentally verified fact and nothing else. The way nature is the way nature is. And what we are trying to do in physics and chemistry and all the other sciences, all of which, if you have not recognized such, emanate from physics and chemistry. What we do is to try to devise experiments and methods of observation to find out how nature behaves. Because as I have said, nature's behavior doesn't give a damn what we think, or what we say, or what we feel, or what we calculate. Never has and never will. Can we affect how nature behaves? Absolutely. Explode hydrogen bombs. That'll change how nature behaves. But thoughts, ideas, theories, and calculations have no impact on nature's behavior whatsoever. So after we do this analysis, we're going to do an experiment involving the saturation of calcium carbonate in 1.0 molar ammonium chloride solution. And then if this pH meter, which I have here, is working properly, we'll observe. We'll measure the pH for that system and see how close it comes to the calculated pH. If the experiment is done properly and the calculated pH agrees with the observed pH, then we have good reason to conclude that our calculation is sound. If the experiment is done properly and the calculated pH is different from the observed pH, then we'll have reason to believe we better alter our calculation. But it's possible that we haven't done the experiment correctly. All these things have to be considered. They're part and parcel of what makes science such a challenging endeavor. But given that, the main purpose by far of science is to help us understand how nature operates. I think it's a very fair statement that in and of itself establishes why science is so doggone important. If we're going to understand the chemistry of life, isn't that part of nature? Sure is. So let's get at it. I hope that what we do, though, doesn't parallel the behavior of the chalkboard, which when I slid this part up to begin my note scrawling on the board, fell apart. There's a big counterweight slider that goes up in here. that keeps the top boards in balance when you slide them up and down so they stay in position. Each now and then this slider falls out. Since I have been on this faculty since 1987 and had the honor of being the first person to lecture in this auditorium, which was 1988, because this building was built in 1988, it has been my unfortunate displeasure to observe that this slider has fallen out of this chalkboard at least 25 times. I am curious why the University of Florida, with all the money which it has to fund all this high-powered research, can't buy a damn chalkboard that doesn't fall apart. In any case, let's proceed. Here's the issue. Here's the equilibrium system which is established. We calculated K for this system yesterday. Here's the chemical version of the equilibrium constant. We already recognize, or we recognized before we attacked the calculation, that S is the molarity of calcium ion, the solubility of calcium carbonate. Because when calcium ion goes in the solution, the calcium ion engages in no further chemistry. After calcium ion goes into solution, in this case by this reaction, then the calcium ion, practically speaking, behaves like a spectator ion. So if we're going to solve for the solubility of calcium carbonate using this equilibrium constant expression, we have to know how the bicarbonate ion molarity relates to S and how the ammonia molarity relates to S. So to simulate that, for the bicarb molarity I wrote in question mark, and for the ammonia molarity I wrote in 2 question marks. So the equilibrium molarity of ammonium ion will be 1.0, the initial molarity, the label on the bottle, less the value for 2 question marks, because that simulates the ammonia molarity. That's material balance for ammonium ion. Is it possible that to grapple with this, we might need to consider charge balance? Is that possible? Sure, it's possible. If we cannot establish a relationship relating these 2 materials to S, then these 2 materials will remain as unknowns. So we're going to have 3 unknowns. And we're going to have to invoke charge balance to crack it. You'll see that analysis because I've already done that. In fact, I was kind enough to my students in summer 2011 to ask them to do this calculation on a bonus quiz. You know me. On bonus quizzes, anything is fair game, so long as it's chemistry related to what we do in this gathering. But there are no limitations that I place on the difficulty factor. So first I pose the question, for this system, is it likely that the bicarb concentration and the ammonia concentration are not only essentially equal to each other, they're also equal to S? Well, let's think about that. First of all, calcium carbonate, water. The carbonate ion hydrolysis extent is 70%. In this case, carbonate ion is reacting with ammonium ion. Will ammonium ion react with carbonate ion far more effectively than water reacts with carbonate ion? Absolutely. Ammonium ion is not a strong acid whatsoever, but it's a whole lot stronger than water. Ka ammonium ion, 5.6 times 10 to minus 10, a very tiny value. But Ka water, 1.8 times 10 to minus 16, a much tinier value. So is it, based on these facts, is it reasonable to believe that carbonate ion will convert essentially completely to this? Is that possible? Sure. I mean, we have ammonium ion solution. We know that's an acidic system relative to water, much more acidic relative to water. So if carbonate ion goes 70% in water, and if carbonate ion disappears essentially entirely at pH 8, we already have done that analysis. We want to take advantage of what we already know in tackling this. Don't tackle it like a problem about which we know nothing. That's not true. Do you think that saturated calcium carbonate in ammonium ion, which is what ammonium ion solution, which is what we're preparing, you think it's possible that the resultant system pH will be less than 8? Well, if the resultant system pH is less than 8, there certainly isn't going to be any carbonate ion in there to speak of. Now, we also know that from an extent analysis standpoint, carbonate ion water, small extent reaction, but carbonate ion ammonium ion is a large extent reaction. That fits with what we just said, that we shall expect no carbonate ion to be present at any molarity of consequence in this system after it is prepared. However, what about the possibility of bicarb ion reacting further with ammonium ion and being converted to H2CO3? Well, we know from a Ka comparison standpoint, I've written the Ka values here, for reactant acid ammonium ion, product acid H2CO3, to recognize that product acid H2CO3 is a good deal stronger than reactant acid ammonium ion. So on that basis, we expect this reaction to have an extent which is quite small. But don't forget the gang-up factor. Early on in chapter 18, did you read about the gang-up factor, which is in the notes? I'll tell you a story about the gang-up factor, because you know I like to tell stories. How many of you are familiar with Muhammad Ali? Now, back in the days of the Vietnam conflict, which I think really is a serious black eye on the history of the United States, Muhammad Ali spoke out against this conflict. By my draft board, I was labeled 1A or A1 or whatever the heck you're labeled when you're fit to serve. But my draft board was Lucas County, Ohio. Toledo is in Lucas County, Ohio, because I was born and raised in Toledo. And when I had to be, or when I was subject to consideration for military service, I was an undergraduate at the University of Toledo. Fortunately, at least I guess it's arguably to be fortunate, my draft board made a proclamation, because draft boards are autonomous entities. At least they were at that time. My draft board made a proclamation that if you were a full-time university student and had a C average or better, even though you were 1A status, you didn't have to go to the military. So I got out. Had that not happened, I wouldn't have resisted, I would have went. Even though my convictions were that this Vietnam conflict, not correct. In any case, back to Muhammad Ali. The point that I want to make about him regarding the gang-up factor is that even though I don't like this, I don't think much of boxing as a sport. I don't think much of any activity where the object of participants is to pummel each other. But Muhammad Ali was rather an artist at this. He was quite gifted at this skill. Consequently, I conclude that if he were here today and in his prime, if any one of us, if any Gator football player, regardless of how strong the person might be, were to get in the ring with Muhammad Ali on a one-on-one basis, no chance. Pop, pop, gone. But doggone it, if the whole bunch of us jump in there with all the Gator football players, I have a feeling that sooner or later we'd overwhelm him because of the gang-up factor. 30, 40, 60 of us might be conked out during the process. But eventually we'd overcome because there are just so many of us. And in this system, do you recognize that ammonium ion is by far the principal species that's part and parcel of this equilibrium system? The calcium ion molarity is going to be small, the bicarb molarity is small, the ammonium molarity is small, but the ammonium ion molarity is quite large. So if the ammonium ion is in there quite large, there might be an observable conversion of bicarb to H2CO3. That's the gang-up factor in action. Do you think it's fair for me to make the statement that the calcium ion molarity is quite small? Well, remember, here's the K value. Now, when we calculated the K value, because I said, keep in mind what we already know when we attack this system. When we calculated the K value for calcium carbonate plus water, we got a value of 1.3 times 10 to minus 12. And a corresponding calcium ion solubility, depending on pH, which wasn't very great. Until we got the pH to 6. Then the pH was fairly substantial. Then the solubility was fairly substantial. Calcium ion molarity was fairly substantial. But here for this system, I got this K value. This is not a big value at all. So this thing is telling us that even though the solubility of calcium carbonate in ammonium chloride solution is certainly greater than the solubility of calcium carbonate in straight water, because ammonium ion is a much stronger acid than straight water, calcium carbonate isn't very soluble in ammonium ion system. That K value is very small, and it tells us that. So we've already cast the argument. How did what? We did that last time. Yes. So we've already cast the argument that conversion of carbonate to bicarb is surely complete. And then we've asked the question, is there any further conversion of bicarb perhaps to H2CO3? We'll look at that possibility later. We've so far discussed it as a possibility. Now, what about ammonia? Well, ammonium ion with carbonate ion is a large extent reaction, so clearly establishing this equilibrium is for this system going to be the principal source of ammonia. Is there any other way ammonia can be produced in this system beside the reaction we have on the board? See, before we do any calculation, I want you to think about the chemistry of the system. Sure. Isn't water certainly the principal species in any aqueous system? And ammonium ion is the principal species. So it's entirely possible. We'll add that to what we have here. Also possible that this reaction now, let's get at the business of finding out In other words, finding out, if we have to pay attention to these considerations, and finding out about the validity of this solubility of this solution for the solubility of calcium carbonate, where we're taking bicarbonate to be the only principal carbonate containing species in the system after this equilibrium reaction is established, and that the only source of consequence of ammonia in this system is also this reaction and no other reaction. If that's true, then the bicarb molarity and the ammonia molarity are equal to each other as well as being equal to S. All right? Now, based on that, we've got the K value over there, 7.2 times 10 to the minus 8. The arithmetic which follows is then simple because we are operating on the basis that the calcium ion, bicarb molarity, and ammonia molarity are each equal to the solubility of calcium carbonate. We know that's true for the calcium ion molarity. That gives us a solubility of 4.2 times 10 to the minus 3. Now, if we think back in our mind's eye, we know that the solubility of calcium carbonate in straight water is 1.4 times 10 to the minus 4. And we know the solubility of calcium carbonate in this system got to be greater than that. This value is greater than that. Now, just for fun, CaCO3 at pH 8.00. We did this one too. Anybody remember the value we got? Look it up. It's in the notes. What have you got? 1.1 times 10 to the minus 3. Now, if this calculation is true, we know that the pH of the ammonium chloride solution saturated with calcium carbonate compares how to 8? If this is true, given that we know this is true, if this is true, after we prepare the ammonium chloride solution saturated with calcium carbonate, how must the pH of the ammonium chloride calcium carbonate saturated solution system compare to 8.00? It has to be lower. Why?
Because it has greater solubility.
Greater solubility. That means this system has got to be more acidic or less acidic?
More acidic.
More acidic. That's right. Now, since we also did this, let's write it down. What do we get for this one? We did this last time. You know me, everything we do in here, you're responsible for. Now, I wouldn't hold you responsible for remembering this information, but if you need it on a quiz or exam, I'd give it to you. Your job is to know what it means. What do we get for this? We did it last time. What do we get? Something times 10 to minus 2. Well, 2.1? Okay. So now we know, if this is true, the pH of this resulting saturated solution system, which we have yet to prepare, will be greater than 6.00. Okay? Now, from this, I have written here, based on this solubility, taking S to represent the concentration of each component of this equilibrium system. Based on this, what's the system pH? How can we calculate it? How can we calculate it?
Well, since the original equilibrium doesn't produce hydronium,
It doesn't have any hydronium ion in it, so we got to go someplace else for pH calculation.
you have to react the H4n plus with water.
Do you think that reaction is occurring in this system?
Yes.
You're damn right. So, we'll write to calc pH, can consider Ka ammonium ion. That's what you just told me. Is there anything else we could consider? Is there another way we could get at pH by calculation? What is this other way? Sure. Did you say carbonate or bicarb? Why don't we take bicarb? Because we recognize that bicarb is a principal species in the system. Carbonate ion is not. Well,
Do we have to consider both at the same time?
what is that?
Do we have to consider both at the same time?
No. We got one solution. It's only got one pH. I don't care which equilibrium we consider, we're going to get the same pH, regardless of the calculation we do to get such. I'll write down etc. You could also use Ka bicarb. Who cares? Now let's make some measurements before we look at the calculation. I would like an observer. Who wants to be an observer? Come on.
Me?
Yeah.
Okay.
You will not only be an observer, you will be a reporter to the class.
Okay.
Come here. Now, quick, fast. I am here observing with this electrode and this pH meter. The pH for 1.0 molar ammonium chloride solution. Now I made this 1.0 molar ammonium chloride solution at the beginning of summer. But it's been in a stored bottle. It should still be all right. But I don't know. Did somebody open the bottle when I wasn't looking and put some foul thing in there? I don't know. I doubt that, but I don't know.
Has that ever happened?
Read.
5.35 pH.
Not me. Read to them.
It says on the pH meter that it's 5.35 pH.
We have OBS pH for 1.0 molar ammonium chloride solution equal to 5.35. What do you think about the validity of this observation? Now then, right now, quick and fast, without pens or pencils or scratch paper or calculators, let's gee whiz the pH for 1.0 molar ammonium chloride solution. Come on, let's go. Ammonium ion plus water, double arrows, hydronium ion, ammonia. Okay so far? Ka, ammonium ion, because that equilibrium corresponds to Ka ammonium ion. It's on the board, 5.6 times 10 to the minus 10. So we got 5.6 times 10 to the minus 10 equals x squared over 1.0 minus x. And 5.6 times 10 to the minus 10 is a daggone small number. So we should realize that for this quadratic, 5.6 times 10 to the minus 10 is equal to x squared. Right? Because 1.0 minus x is going to equal 1.0. And x squared divided by 1.0, it's x squared. Square root of 5.6 times 10 to the minus 10. Roughly. Something times 10 to the minus 5. Give me a gee whiz on the something.
2.2.
2.2, a little bigger. 2.5, a little smaller. That's all right, you're in the ball game. I get 2.36 to 3 sig figs, so I'll take 2.4. All right? So I'll write down hydronium ion calc. It's 2.4 times 10 to the minus 5. What's pH? pH is 5 less the log of 2.4. The log of 2 is 0.3010. Log of 3 is 0.4771. And 2.4 is closer to 2 than it is to 3. Be surprised how quickly you can do a lot of this stuff if you memorize some of this information, like I have. So I'm going to get a pH that's on the order of 9 point. Three? 9.5. Well, I'm going to be subtracting about 0.4. About 9.6. 9.5, something like that. Okay? Oh, say 9. What did I say? 9. 4, pardon me. 5 less the log of 2.4. Where does 9 come from? Who said 9?
That was me. Sorry.
Okay.
Do I go back?
No. Now, we're gee-whizzing the pH to be about 4.6, 4.7, something like that. We got an observed pH of 5.35. Something's out of whack. Now,
It went down to 5.34.
I went to 5.34, but we're still a long way from something on the order of 4.6, 4.7. All right? Now you can have a seat for a moment, and then we're going to prepare the other system.
Okay.
Okay? So, what adjustments could we make as we proceed with this investigation? Well, I can say the calculated pH is 4 point, I think I wrote it down what it is to 2 sig figs. Let's see. I can't find it directly in all my scribbles.
You can write it in the bottle if you didn't have it on your notes.
Well, what I have, 4.63. Thank you. I forgot I wrote it on the bottle. Okay. Tell me, in Chemistry 2045, did you hear anything about activities? I'm curious. Did you hear anything about activities? Do you know that a 1 molar solution is pretty concentrated? Do you know that in a fairly concentrated solution, ions, which are oppositely charged, have a habit of sticking together rather than floating around separately? Because in a fairly concentrated solution, they're close. So the charge densities drives them to stick together. Activity I call effective concentration. for a solution of an ionic solute. The effective concentration of ionic solute is a measure of how many ions are in fact in the solution, traveling around on an individual basis rather than traveling around stuck to each other. This solution is fairly concentrated. So it's entirely possible that because of the high concentration of this solution, we're observing a pH that's considerably higher than the true pH. Is there a way by which we could correct? Yeah, we could say, well, if I want to correct this pH, which I observe, to this pH, which is true, I got to subtract this number from this number to see what the deviation is. Well, this subtracted from this is what, about 0.7, something like that? Well, that means when I prepare the ammonium chloride solution saturated with calcium carbonate, the pH which I observe, I might have to subtract 0.7 from to get the true pH. All these things are things we have to think about. These are things which I couldn't possibly hold you responsible for at this stage of the game because you haven't been in the laboratory doing any of this stuff. But this is the kind of stuff which chemists have to think about. So let's make the system. And while the system equilibrates, we'll do the calculation. So what I'm going to do is to take a scoopful of calcium carbonate, put it in the beaker. Don't need much because there's not much that's going to dissolve. What now is going to happen to pH? pH going to go up, stay the same, come down. I'm going to increase the stirring speed. It's 6.67 now and going up. We can rest assured that by observation we will get the equilibrium pH when the pH reading becomes constant. Okay? Now let's do the calculation. Here's what we want to calculate. So in order to calculate this, we have to evaluate this term and this term. Well, we've done that. What is the value for this term? Based on what we have done. There it is. 4.2 times 10 to the minus 3. And this is 1.0 minus 4.2 times 10 to the minus 3. Now, practically speaking, that keeps this as 1.0. But I'll put this in there and I'll go back to two significant figures after I do the calculation. Now I've done this calculation and I get a hydronium ion concentration of 1.3 times 10 to the minus 7, which corresponds to a pH of 6.89. Well, that's keeping with some of the considerations we've already made. We well expect the pH to be less than 8 but greater than 6, as it follows from facts we've already thought about. We're up to 705. $706. Now, what we need to do is to wait for this system to equilibrate. I will allow this system to equilibrate and report its value to you. And in preparation for our next gathering, because I believe the pH we observe for this ammonium chloride solution is much higher than it should be, independent of activity effects. So I'm going to make some new 1.0 molar ammonium chloride solution, reobserve the pH for that, and then we'll pursue this further at the start of next gathering and see what we get.